Well, it's great to see all of you this afternoon. My name is Heather Holbach. I have a somewhat unique position with Noaa. I am employed by Florida State University, which is right here in Tallahassee. I sit at the Center for Ocean Atmospheric Prediction Studies, which is in Innovation Park, which is the research campus in Tallahassee. But I'm also a Noaa Cooperative Institute employee. You may have heard of cooperative institutes as well. These are institutes that allow Noaa to fund research through universities. And the Noaa lab that I'm partnered with through the Northern Gulf Institute is the Atlantic Oceanographic and Meteorological Laboratory, which is down in Miami, Florida. With this, it gives me the opportunity to participate directly with Noaa research topics, and I get to have a direct impact on research to operations through AOML. All right. Let's see. We need to click on this one. There we go. All right. So my goal with this presentation is to give you an overview of the research that is done at the Noaa lab that I work with, and in particular, the Hurricane Research Division that is housed within AOML. There's also a physical oceanography division, a chemical oceanography division. Within HRD, I play a role that's focused on observing the surface of the ocean under hurricanes. So I'll give an overview of the research that is done within HRD, and then I'll give you a little bit more specifics on some of the topics I look at myself. HRD is down in Miami. It sits on Virginia Key, right across from the University of Miami's Rosenstiel School for Marine and Atmospheric Sciences. So it's a great location for them to collaborate with students at Rasmus. The primary objectives for HRD are to advance basic physical understanding and improve forecasts of tropical cyclones. And we have access to a very unique resource to be able to tackle these topics, and that is the Noaa aircraft research facilities. So we have 2 aircraft that I'll talk about that we have access to for conducting research experiments to try and understand different topics about tropical cyclones better, with the end goal of improving the forecasts and understanding of them. But within this broad context, we have a few specific focus areas. One is to improve observing techniques. So we do a lot of work that helps with collecting direct observations that then we can feed up the chain to satellites. We do a lot of modeling and prediction studies. So we have the next generation regional modeling for hurricanes that's being done at HRD called CAPS. And then we also do a lot of data assimilation. So we collect all these observations, but we need to understand how to best assimilate those into the models to get the most impact in your results from the models. And then we also, more directly want to understand the dynamical and physical processes. So how do tropical cyclones actually work? Because we need to understand that so we can feed that into the models as well. And then we also want to understand more about hurricane impacts. So of course, that's why we all do what we do, is so that we can understand how or what sort of impacts these tropical cyclones might have, and then be able to inform the public how to better prepare themselves for this. So going more into our field program that we hold every year, it's called Advancing the Prediction of Hurricanes Experiment. It used to be called IFEX up until about last year. That was the Intensity Forecast Experiment. But we're evolving it over time. So we have 3 main goals for our field program to address the topics that we just talked about. The first is focused on that model initialization and evaluation. So we want to collect observations that span the whole TC life cycle so that we understand, how things impact tropical cyclones from the very beginning to the very end. And then goal 2, which is the one that I focus on the most, is directed more at the measurement strategies and technologies. So we want to test instruments, figure out what we can do to improve the observations that we're collecting. And then, we target different intensity structures and also focus on some of the hazards with that. And then our third goal is targeting more of the physical processes. So how can we collect observations that will help us understand a certain process that's occurring within the tropical cyclone? And we have this data available all the way back to 1960. So these aircraft we've been flying aircraft into tropical cyclones for quite a while. But the most recent workhorses that we have, the P3s, have been around since the mid-70s. All right, so I want to introduce the aircraft to you so you can kind of understand what sort of resources NOAA has available for these sorts of projects. So the NOAA WP3D Orion, or P3 for short, as you most likely hear it, NOAA has 2 of these aircraft right now. We affectionately refer to them as Kermit and Miss Piggy. And yes, Jim Henson did make those for us. These are our workhorse. So these are the aircraft that fly low and directly through the storm. They penetrate the eye wall, get right into the center. And the picture on the right shows the view from one of the workstations I would sit at when I'm on the aircraft. So you can see there's a lot of scientific equipment, a lot of computers, and you can actually go all the way up to the cockpit if you want, as long as that seatbelt light isn't on. If that's on, you want to be in your seat. So one of the benefits of the P3 compared to the Air Force C-130 Hurricane Hunter aircraft is we can put so much extra research instrumentation on these aircraft. So this is an example of some of the instrumentation that we have on the aircraft. So we have microphysics probes, so we can understand more about the precipitation and ice particles that are in the atmosphere where we're flying. We have 3 different radars. I have 2 pointed out here. We have the tail Doppler radar. This is probably the most significant different instrument that we have on the NOAA aircraft. That instrument allows you to get basically a CAT scan of the hurricane as you're flying through. So it's getting a 3-dimensional look at the precipitation and wind structure in the hurricane. So the Air Force planes can't have that because they have the cargo bay on a C-130, so you can't put it onto the tail, but with the P3 we can. We also have our multi-mode radar or lower fuselage radar. This is our belly radar mounted on the bottom of the plane. It's more similar to what you're used to looking at from the ground-based radars. It's doing a horizontal scan. This radar gives us quite a bit of detail right around the plane, so we can see more cellular features that might be around us. We also have dropsondes, which are released from the aircraft. I'll talk about those a little bit more later. The step frequency microwave radiometer, or SFMR, that's the instrument that I'm responsible for at HRD. So a lot of the research I'll talk about later is going to be related to the SFMR. And then we also have an experimental port on the bottom of the plane that can house a variety of different instruments. Lately, we've had it housing either the wide swath radar altimeter, which is getting surface wave data, or the imaging wind and rain profiler IRAP, which is getting, it's similar to a scatterometer, but it can get a vertical profile of winds as well. All right, so a typical flight with the P3. We typically, in non-COVID years, have about 15 to 20 crew members on board. This got down to as low as 8 during 2020, I believe. But we have, pilots, we have a navigator, we have flight engineers, we have the flight directors, which are the meteorologists in charge of safety for the flight. And then they also have a lot of data technicians because we have a lot of instruments. So you need to have people that can troubleshoot them when you have ever you have an issue. And then from HRD, we usually have 2 or 3 scientists on board. Our roles are to direct the research and make sure that we're collecting data in regions we want to target. We have somebody who's processing the dropsons. They require a little extra quality control before we send them off the aircraft. And then we usually have a scientist that's making sure the radar data is being collected and sent off the plane properly. So the other aircraft that we have is the Noaa G4 Jet. So if you might have noticed, the P3 was a prop plane. You don't want to fly a jet through a hurricane because it doesn't respond as quickly to changes in power input as a prop plane does. So when you're going through turbulence, you need to be able to constantly be adjusting the amount of power you're sending to all of the engines to keep the plane as level as possible. And you can't do that with a jet. And also when you're flying through heavy precipitation, that can have some more significant issues on the jet engines. So the biggest advantage of this aircraft is we can sample up high and around a tropical cyclone. So we can get information about the environment out ahead of a storm, for example. If there's a lot of dry air, it's really helpful to know that so that the models can then have a better chance at producing a more accurate forecast. The G4 does also have a tail Doppler radar on it, which makes it unique. And then it doesn't have nearly as much instrumentation, but it does collect flight level observations, and it's able to release dropsons as well. And what we're finding is that getting those dropson observations in the higher altitudes is really important because just small changes in the relative humidity in those levels seems to be making a pretty big impact on forecasts. It also has an SPMR. Unfortunately, it hasn't been working properly. So we're hoping this aircraft is in the process of being replaced with a G550, which should be coming online in 2024 is our hope. And that will have some more instrumentation than this and hopefully a working SPMR. All right, so back to the field program. So our experiments are divided up into different stages. So we want to target, we have different experiments to target different stages of the life cycle of the storm. So we have genesis experiments. Genesis is often overlooked and it can be very difficult to study, but what we're finding is it's very important to get those early stages of development correct so that that's where we can get a lot more improvement in models, especially for these storms that develop and reach land in just a couple of days. It's really important to be able to understand that genesis process. We also have experiments focused on the early stage, so tropical storm or category 1 strength, mature stage, so that's your category 2 and higher, major hurricanes, and then also end stage, so storms that are making landfall or undergoing rapid weakening or extratropical transition. In addition, we also have some experiments where we partner with the Physical Oceanography Division and other external partners to collect observations of the ocean, both before and after a hurricane has passed over a certain location. As we all know, hurricanes get a lot of their energy from the ocean, so it's really important to not only study the atmosphere, but also the ocean. And then, as I alluded to earlier, we also do a lot of experiments to help with satellite validation. So now transitioning a little bit to more of the research topics that I address using observations collected by the Hurricane Hunter aircraft. I use dropsons in a lot of my research. This is one of the few instruments that is able to give us in situ or direct observations within the hurricane. So we release these through this tube that's in the plane. They fall out of the bottom of the aircraft, and then a small parachute deploys. This parachute helps stabilize them as they're falling through the atmosphere. They're collecting information on pressure, temperature, humidity. They also have a GPS sensor in them, so we get the location. And from that change in location, we can get wind speed and wind direction from them. So one of the topics I've been revisiting lately is the flight level wind reduction. So this is, I don't know if you've ever heard of the 90% rule, but the Hurricane Center for many years has used the 90% rule as a way to reduce wind observations that were taken at the altitude that the aircraft was flying at to the surface. And so we're finding that that doesn't always match with some of our more direct observations at the surface or those from the SFMR. And so I'm trying to get an understanding of how much variability is in that 90% rule. So this graphic shows you the profiles from dropsons in the gray lines plotted against height. And then the x-axis is the wind speed from that dropson normalized by its 850 millibar wind speed, which is one of the flight altitudes we might fly at. And so if you focus on the line that's 10 meters, you see that blue point is at about 0.885, I believe it is, for 850 millibars. That's what you would multiply the flight level wind speed by to reduce it to the surface. That's what's been historically used. But if you look at the red points, that's the interquartile range for these profiles. So we're seeing that the spread of the middle 50% of the data is much larger than that one value might indicate. And then we're also looking at it for the W150, which is the lowest 150 meter layer of the dropson profile, and reducing that to the surface. And the spread in these dots illustrates the same sort of thing, is there's a lot of variability in this. All right, so the SFMR. So we like to affectionately call the SFMR the Smurf. It's a passive microwave sensor. It's responding to changes in white water at the ocean surface and rain in the atmosphere below the aircraft. It retrieves surface wind speed and rain rate. And like I said earlier, it's on both the Air Force and NOAA Hurricane Center aircraft. So here I've included some pictures that I've taken from the P3 that show you how much the surface changes with wind speed. So this is the relationship that the SFMR is relying on. So we've recently noticed some discrepancies, like I alluded to before, in the different observations that we can get of surface wind speed. So the upside down red triangles, if you look at near the peak, this is for Hurricane Dorian. This is from the National Hurricane Center's best track, their tropical cyclone report. You can see that the SFMR, which is those upside down red triangles, starts to separate from the rest of the data. So we're trying to understand why. So we're updating some of the research and algorithm development that's been done for the SFMR in the past. And we compare it to dropsons. So that's why I said I use dropsons a lot. That's our surface truth that we have to compare it to. And so if you look at the really high wind speeds, so 50 meters per second or higher, you start to see that those dots are mostly above that black 1-to-1 line. And so the area that we're trying to address within the SFMR algorithm is what we call the wind-induced emissivity curve. It's not super important that you understand and interpret this graph all the way, but basically the black line there is the best fit to the new data set. And the other two lines are what were used previously. But one of the things we're finding with this newest data set is that there is a lot more impact from rain than we're accounting for in the algorithm. So we're trying to update that. And one of the ways that we're doing that is by trying to use data from the tail Doppler radar on rain rate. But there's another issue that we've encountered, and that's that the tail Doppler radar reflectivity, which is what we use to convert to rain rate, has never been calibrated. So we're trying to figure out how to overcome that challenge. And one of the other issues we have is drop-ons move after you drop them, especially in the eyewall. The rainbow color is the SMR along the flight track. The copper color is how the drop-on was moving as it fell. And so you can see that it moves quite a ways away from the flight track and where the SMR is. So you could be getting some errors when you're trying to compare the SMR to the drop-ons. And so what we're trying to do is we'll drop a bunch of them in a row as we fly in through the eyewall, and then we go and fly over where they splash so that we can try and get a more direct comparison. All right, and then one last thing on the research I'm doing is focusing on ocean surface waves. We're trying to understand how the waves change around the storm. And so we've got this really cool instrument, the WSRA, that gives us ocean surface wave directional spectra. So the last thing I wanted to share was, how did I get involved with NOAA? I think a lot of you students might be interested in that. So it all started when I was working on my master's. We had a NOAA scientist sitting at COAPS, which is where I still work. And he served on my master's and PhD committees. When I finished up, he, during that time, let me backtrack a little. So during my master's defense, he's like, so what do you want to do next? I'm like, do you want to fly? He's asked me, do you want to fly hurricanes? I was like, well, yeah, who doesn't? A lot of people don't. And so he got me in contact with another scientist at AOML, and I did internships during my PhD with him. And then when I graduated, I started a postdoc through NGI, and then I transitioned to research faculty and continued working as a CI employee. So there's multiple ways to get into NOAA, but it's really about the relationships you build throughout your career and who you meet that has been really important for me. And with that, I'll leave this video.
It was rated to a category 5. As you can see, this image hasn't really changed much. It's a little old and hasn't changed much over the last several hours. It's a strong storm. It's intensified slightly since Noaa G4 Jet left.
Very quick questions.
Just one question. You have those sensors on some medical equipment. What is measured?
So it's primarily measuring the drop size. So it gets information about the different sizes of particles and the concentration.
One of the ice.
So some of the probes can do liquid and some do ice.
One quick question for me. You know that the wind speed varies at latitude. Full purpose. Why not choose wind speed within a layer instead of 850 hectopascal?
So that's where we're trying to get the Hurricane Center away from trying to use that like 850 millibar.
It's very noisy.
Yeah. And we're trying to understand more about that variability and how each of the different instruments, because of their observing characteristics, how that changes between instruments as well.
Yeah, that's right. Okay.
But yeah.
Thank you. Excellent presentation. Okay.
I just want to know, how does it feel to fly through one, through the hood?
Well, most of the time it's pretty, benign, like flying on a commercial, most of the time we spend flying to it. But flying through the eyewall, sometimes it's no different than anywhere else in the storm, but other times you can leave your seat for a few seconds, but we're strapped in and we've got the best pilots and flight engineers and crew that you can have.
Okay. Thank you so very much.